Okay, fam, we are on chapter 7. This is the last chapter of the semester, and I'm giving away all the goods here, but I am going to focus most of my attention on this video today, right here. Sampling distribution versus population distribution. Once again, look at how beautiful this reading guide that I filled out is, with highlighting and notes to myself and little things off to the side and whatever. So anyways, I'm going to talk today about big difference between sampling distribution and population distribution. That is the main thing I want you to take away from this introductory video. Apologies for my absence today, but we can still power through this first day so I can talk to you about what's going to be really important for this chapter. And the thing that is very noteworthy about chapter 7 is that it is extremely important for success in next semester. Next semester is extremely cumulative. Chapter 8 relates to Chapter 9. Chapter 10 is a combination of 8 and 9. Chapter 11 is a follow-up to Chapter 10. Every single thing we do second semester starts with these two vocab words. So don't just glaze over this and give me some half effort, because this is going to be crucial for success second semester, okay? Let me first zoom in on this picture that I drew. So let me zoom out. I've got population distribution here, sampling distribution here, and I'm going to spend the bulk of my time discussing this image. So you'll have plenty of time to copy down, screenshot, insert, whatever you want to do. But I want to talk to you first about this thing called a population distribution. This is something that we could have put on the board in August. This is a population distribution of shoe size. Notice I have a quantitative x-axis here, and we could have had every single one of you. In fact, I would have loved to have done this today had I been there. Everybody come up and put a dot on the board what your shoe size is. And it looks like I asked 44 people. I just made this up because I want to do this together, but we can't. I asked 44 people across my 2 stats classes, and it looks like the smallest foot in any of my stats classes is a size 6. And it looks like the biggest foot in any of my stats classes is a size 14. And all the other students fell somewhere in between. And it looks like the average, center, mean / median, because this does look approximately normally distributed, is a size 10. Okay, and I need you to understand, and I need you to remember back from chapter 1 when we first started talking about dot plots. That's what this is. This dot right here represents a dot of one of my students, and it stands for that student's shoe size. I'm guessing based on this dot plot, it's roughly 11. I didn't do a great job labeling my x-axis, but you get the point, okay? I have 44 students. There are 44 dots here, and each dot represents one student. Okay, so Sally has 1 dot, and Jackson has 1 dot, and Stacy has one of these dots, and all of them represent their specific shoe size. We're good? That's review. What the heck does that have to do with a sampling distribution? Okay, great. I have a lot more written over here, but once again, sampling distribution. This is very important. This is our new vocab word. In fact, you guys, this is the title of the chapter, sampling distributions. Ding, ding, ding. Okay, let me explain. What does it mean? Okay, so we've got a sampling distribution, and I have decided to, just because I wanted to, choose n equals 5. It is a sample of 5. And what if I had all of you guys in class right now? What if I randomly put you in groups of 5? Can you picture that for a second? Hear me, okay? Don't be listening to music and talking to your friends. Hear me explain this. Let me put you into groups of 5 randomly. So you're now sitting in the classroom with 4 other friends. And I need you 5 to come up with an average shoe size. Okay, can you picture doing that? So you've got 4 friends around you and you're like, bro, my shoe size is a 12. Oh, my shoe size is really small. I have a 7. Oh, I'm a 6.5. Oh, I'm a 9. And you guys are going to average your 5 shoe sizes together, and you're going to come put a dot on the board for your average. So one of these dots right here represents one group's average shoe size. Let me go back. This is one person's shoe. This dot right here is an average of a group of 5 students. Okay, so you're sitting with your friends, you've got your calculator, you came up with your average, you sent a representative up to the board to put a dot on the board that represents the average shoe size from your group of 5, and then you all turn and you look at me and I say, okay, now get with a different group of 5 and do the same thing. Go. So everybody mixes up again. You got a different group of 5. Now you have a size 6, a size 8, a size 11.5, a 12, and a 13. All in your group. You come up with an average and you come put a dot on the board, and it happens to be right here. Okay, so every single dot in this distribution does not represent one person. It represents an average. Hear me when I say this, an average of one of the groups of 5 people. One important thing to note, make a note to yourself, is that the sample size has to be defined and every single dot has to come from the same sample size. So it is not the case that one of these dots represents a group of 2, one of these dots represents a group of 10. That doesn't work, and that's not how you play the game. The sample size has to be 5. But can you imagine how many different combinations of 5 I can have based on 44 students? Like if I have a group of 5, I can just swap out one person and that's a different group of 5, and that would put a different dot in this dot plot, right? Did you know that there's actually this many possible combinations of groups of 5 if I have 44 people? How did I get that? 44 choose 5, 44 NCR 5. Anyways, so there's actually 1,086,008 dots that should be in this sampling distribution. And no, I did not have time to put that many dots in here, but you get the point. That's why I wrote it there. Why are there so many more dots on the sampling distribution than there are on the population distribution? That's a question that comes up every year. It's a great question, but what I need you guys to know and understand is that the population doesn't have to be a huge, massively large millions and billions number. Okay, if my population is just my 44 stats students, then I only have 44 dots here. No big deal. But I have way more dots over here because there are this many different ways of choosing a group of 5 to come put a dot on the board for their average shoe size amongst that group of 5. There's a bajillion dots here. 1,086,008 actually. Now let's talk about, remember what one of these dots represents. It's one of the averages from a group of 5, but why is this number right here not 6? And why is this number right here not 14? Let's talk about that for a second, because if I take this really teeny tiny foot and I average, I'm assuming her, with 4 other people, isn't it likely that these 4 other people are going to drag the average up above 6? Likely. Probably closer to 8. I'm guessing it's around 8. We will mathematically figure out how to calculate what that number is. But same thing, if I take this person that has the largest foot in stats class, which is a size 14, and I average, I'm assuming him with 4 other people, isn't that average not going to be 14? It's going to be lower. So another thing that I need you to take away from this is the population distribution is more spread out from 6 to 14 than the sampling distribution. And that, my friends, is because the sampling distribution represents averages. Okay? That is something that's really important, and I will continue to refer back to this picture as we talk more and more and more about sampling distributions. But that is the gist, and that is the overall takeaway that I want you to understand. And hopefully you have a decent picture in your notes and that kind of explanation makes sense a little bit. What does one dot in a population distribution represent? It represents one person. One person's whatever we're measuring here, in this case, shoe size. What does one dot in the sampling distribution represent? It represents an average of a group of, it'll be defined, 5 people. We could use 4, we could use 10, we could use 20. It doesn't matter, but it just has to be defined. And that is the number of people that average their shoe size together and then put a dot where that average is. Okay? There's another example here in the book. This is a screenshot. This is not in your notes, but I just wanted to direct your attention. This is page 422, I believe, at the bottom. Here's another example of population distribution. Every single dot here on this dot plot represents a height of somebody. I don't know, it looks like there's maybe 25 people. Maybe that's the heights of everyone in our stats class. We have someone really short. We have a couple people pretty tall. But this is the population distribution, which means every single dot represents a person. And everybody came up and put a dot on the board, a purple dot, that represented their height in inches. And you can see the average here. Here's the sampling distribution, and it's defined as n equals 4. So if I had all of these people get in groups of 4, notice what the smallest average I came up with was. This is not a true sampling distribution because we should have like 25 choose 4, which is a huge number. A lot more dots here. That's why it says approximate sampling distribution. It's not the complete one because there should be a lot more dots. But this is the beginning of a sampling distribution. And look, my smallest average I came up with was over 60. That's because this really short person got averaged with 3 other people. And it brought the lowest number, I guess lowest average, up to above 60. And look at the mean here. This is the mean of the population, 66.07. And the mean of just the beginning here of the sampling distribution is pretty close to that, which is kind of cool. Okay, the range here goes from 54 to 75, which is what, 21? And the range here is much smaller. That matches what I talked to up here, right? Because the tallest person gets averaged with some shorter people, therefore bringing the average height down. Okay, same thing that happened with the shoe size. The smallest foot was 6. The smallest average was not 6 because that really small foot got averaged with bigger feet. Okay. Let me go down. I'm going to skip this. I can't wait to do this example or that problem that I just skipped with you in class tomorrow. But I have just a few things for you to copy down while I talk through. I'm going to skip this for a second because it has to do with what I skipped. But let's talk about bias. You know what bias is? It's when somebody responds not truthfully because they feel pressured or whatever. Bias, for lack of a better word, leads to, it makes me think of inaccuracy. Okay, we have inaccurate results for some reason. And so it occurs in this chapter when the center of the population distribution is not equal to the center of the sampling distribution. I kind of glazed over that thought up here. But look, my average shoe size, this is approximately normal. So the mean and the median are both really close to 10 here. And if you do every single possible group of 5, yes, sometimes your average is going to be overestimated. Sometimes your average is going to be overestimated. But if you include every single possible combination of 5, the mean of the population distribution and the mean of the sampling distribution will be equal. That's one of the things you should have written in your reading guide. And that should make sense too, because it includes every single possible combo of groups of 5. Can you imagine if I had you get in groups of 5 until you ran out of different groups of 5? That would take forever. There would be so many different groups of 5 in class that we could make. But the average for each individual person here is 10, and the average of all the averages will also be 10. That is what this means right here, the average of all the averages of sample size 5. Remember, every dot here represents a sample average of 5 people. And when you average all the averages together, again, it'll be about the same as what it is for the population. We got that right here. The average here is about 66. The average here was really close to that. And that's because not every single dot is present here. This is approximate. Where was I going with that? I kind of went off on a tangent. So that is what I want you to write for bias revisited. When the center of the population distribution is not equal to the center of the sampling distribution. Variability. You can control that by your sample size. Larger samples leads to smaller spread. I have 2 things that I want you to write down here. You gather more info about your population, which gives you more accuracy, which gives you less spread. Your data is going to be less spread out when you average more and more and more people into your sample. More people in the group reduces the impact of one potential outlier. I wanted to kind of go back to that for a second. I'm sorry to keep flipping back and forth. Pause if you need to. But let me talk about the shoe size people. If I average this size 6 person with just one other person, let's say that you have a large foot like me, I do, and I get put together in a group of 2 with someone who has a size 6 shoe. That's going to really impact the average, right? I wear a size 10.5. This person wears a 6. Our average is a little bit over 8. Okay, that really impacted the average. However, what if I average that size 6 shoe with 5 other people? Then that 6 doesn't have as much of an impact on the group of 5 as it did on a group of 2. What if I average this 6 with 19 other people? Then that 6 barely makes a difference. The same thing as test scores, you guys. If you bomb 1 test, but we've only taken 2, your grade sucks, right? But if you bomb 1 test and you've had 20 tests, that bomb doesn't hurt as bad. You get what I'm saying? So anyways, that is what I was referring to when I was talking about more people in the group reduces the impact of one potential outlier. If you just think about the test scores also, if you have one really poor test score, you want to have a bunch more tests for an opportunity to reduce the impact of that bomb on your overall grade, right? A little bit more and then we're finished. Variability is not affected much by population size as long as the population is much larger than the sample. Remember how the sample can't be too big? We talked briefly about this last chapter. We're going to talk about it again this chapter, the 10% condition. As long as you take a sample that is not more than, too big, 10% of your population, then we're good. Bias is related to accuracy. Variability is related to precision. We'll talk a little bit more about that later, but let's get these symbols down. See that little bar over the X? Remember what X bar means? So this mu X bar means the average of all of these samples, which is different from just the mu of X, which is the average of all of the people. Okay, so we have a big difference here. There's one tiny little symbol that very often gets overlooked, so be careful about this. But X bar versus mu of X. Let me go back. The 10 right here is the mu of all of the X's, regular X. The 10 here is the mu of all of the X bars, all of the samples of size 5. That is what I'm talking about when we're looking at those samples right there. Same thing with p hat. We'll talk more about this tomorrow, so don't worry about that. These last two examples, just to summarize the difference between a population and a parameter and the sample and the statistic. You can go ahead and read through these two examples, and I usually save this for a warm-up in class, but the population is all of the bottles at this plant on Tuesday. The parameter is what we are assuming to be true, the 20 ounces, what is claimed by the Arizona tea plant. They're supposed to be filled to 20 ounces. As you know, there's some variability. We take a sample of 50 bottles, and the average for those 50 bottles, we're not expecting it always to be 20 ounces. That is just the given statement. And our 50 bottles might be a little bit different from the entire population. The average is 19.6, so that is our statistic. Notice I've got some symbols I'm using here. The mu goes with the parameter, this X bar goes with the statistic. And remember, the P's go together, the population and the parameter. The 20 ounces is dealing with all bottles. And then we just take a sample, you know what a sample is, 50 bottles, and the average from just that sample apparently is 19.6. We've got one more example down here, New York to Denver flight. The population is all the passengers at the airport, and you select a specific flight, and apparently 8% of the 125 on that flight were selected for random security, but TSA claims that it's 10. So if we take a sample, it's not always going to be 10. Sometimes we get 9, sometimes we get 8, sometimes we get 11. So let's, relay that into our vocab. The population is all the passengers at the airport. The parameter, whatever is claiming to be true by TSA, is the 0.1. We took a sample of 125 people, and for that sample, we got a statistic of 0.08. I'm going to label that as my p hat. Big difference between p, which is the parameter for the entire population, and the p hat, which is based on a sample. Okay, that is your crash course, your introduction to this chapter, and I will answer all your questions. We'll talk a lot more about it tomorrow. Love you guys. Thanks for watching.